So as part of the Introduction to Advanced Experimental Techniques lectures on noise, we're going to look at some of the common sources of noise that you'll encounter in a real experiment. So we're going to discuss thermal noise, sometimes called Johnson-Nyquist noise. We'll also mention quantum noise, so this is a shot noise, or sometimes called flicker noise. And we'll mention 1/f noise. And then these are all sorts of intrinsic sources of noise that there's a limit to what you can do about them. But then to finish off, we'll also talk about some of the sorts of noise you can get or interference you can get from things that you might be able to control in your setup. So let's start off first of all with thermal noise. So this is what happens when you have a resistor. And of course, in any kind of real electrical instrument, you're going to have resistance there. You can't really get away with it. So what's going on here is we have some kind of current flow going through this resistor, and then coming out of it, you've got the current. But what you find is that as that current passes through that resistor, something is happening, which means that you're getting an additional voltage drop on top of what you expect from Ohm's law. You're getting some kind of fluctuation in voltages, which of course is a noise. So what's going on here? Well, we can actually think about what's happening here. Okay, so to think about what's going to go on with this resistor and how it can introduce some noise to our circuit. Well, let's start off by just thinking about the resistor. So it's got some current coming into it, it's got some current going out of it, and it's got a resistance R. Well, the first thing we might think is that if we took a look at what was going on inside this resistor, then if it was, say, a metal, for example, it would have a series of electrons, and we know that those electrons are in constant motion. And we also know that if you're at a finite temperature, then you expect some of those electrons to speed up slightly. And if we're at a sufficiently high temperature and we think about what's going on, we can simply treat these electrons like they're a gas. So this is a free electron type model, and we can equate the kinetic energy of the electrons with thermal energy of kBt. And so we can show that the RMS velocity, so the average of the square velocity square rooted, is just going to be kBt over m. Okay, and we can then think, okay, that's fine, but because these are charged particles we're talking about, that's going to imply that we're going to have an RMS current as well. So that implies that we can write down an RMS current, which is going to be simply given through the Drude formula by the density of electrons times their cross-sectional area times their charge times the RMS velocity. Okay, so now we want to think about what's actually going on here. So of course this RMS current isn't necessarily coming external to the resistor. This is just these electrons are all confined within this resistor, and they're saying these are oscillating backwards and forwards a little bit. And that's going to have an effect on the voltage drop we measure across this resistor. So to analyze what's going to go on there, we're going to replace the single resistor with an equivalent network. So what we're going to have instead is two resistors, each of which is going to have a resistance of 2R. So each of these resistances is going to, we can think of as having a little fluctuating current there. So what's going to happen is we can think about the effect of the current fluctuations that happen in this resistor and what happens with this resistor. So let's call this 1, let's call this 2. So what happens is we get some fluctuation in currents due to the electrons in this resistor. That current's going to go round the loop, backwards and forwards like that, and that's going to cause some voltage drop in resistor 2. And we can write down what that is, because we can simply say that the RMS voltage is going to be the RMS current times the resistor, resistor 2. I've given that 2R so that you make sure that when you add them up together, you get the same resistance R. So that also means you're going to have some power being dissipated in your circuit as well. So you're going to have an RMS power, which is going to be the RMS voltage squared over the resistance, which is 2R. And so that's going to give you a power of 2 times the RMS voltage, 2R times the RMS voltage. Now that's the power in resistor 2. So the total power is going to be just double that because we've just done it for that resistor. Now we need to think about what happens to the current fluctuations here, giving a voltage here, which then dissipates some power on that side. And so the total RMS power becomes 4R times, I should put squared, of course, the RMS voltage squared. Okay, so now what we're going to go and do is we're going to stop and think about is another way we're going to get to the power that's being dissipated. Okay, so we have our pair of resistors in a little loop like this, and we have some fluctuating voltages across here because of the fluctuations in the current. Now, what we need to think about is that what we've effectively got here is a little oscillating electromagnetic radiation that's confined to a loop. And so we can think about this in terms of the modes of those vibrations that are going to be permitted. So just like thinking about a wave in a box or a particle in a box, you can think about the boundary conditions. Well, the boundary conditions would be that the oscillation is continuous. So in other words, that whatever the size of this loop is, you have to fit an integer number of wavelengths around that loop for that to be a valid vibration mode of the system. And we'd also think that, well, this is a macroscopic system, and so there are many different modes. If you think about those individual modes, then when you write down the constraint for the wavelength, has to be you have to have a number of wavelengths within the box. That essentially tells you that those modes are going to be spaced equally in frequency. So we can write down the amount of energy that you would get in an electromagnetic mode stored that's confined to this ring, which obviously represents our resistor. So we can say that the energy per mode is going to simply be given by h bar omega over e to the h bar omega over kt minus 1. And then so this is the energy per mode, and this is the probability that that mode is occupied. And then we note that we're in a regime where we can expect reasonably h bar omega to be much, much smaller than kt. So therefore that we can rewrite this h bar omega over 1 plus h bar omega over kt plus some higher order terms minus 1. And that is approximately, oops, let's make that kb, approximately kBt per mode. Okay, so we can then note that, as we said, that those modes are spaced by some frequency. So each mode has a frequency, and the separation, so it's a frequency f, and it's separated by delta f, and delta f depends on the jump, depends on the size. So that depends on the size of the resistor or the cavity. Okay, but what we can say, it doesn't really matter how big or small delta f is, and you're expecting it to be very, very small because it's the maxed off cavity. What you can say is that if you think about the energy multiplied by in terms of its the energy distributed over different bands of frequencies. What we're saying here is we have some kind of energy versus frequency, and you have an array of modes. Each one of those contains kt, and the separation is delta f. And so you can work out the total energy we've got per mode, and that's simply going to be the energy for the mode times the width of the mode. And so you can write down an energy or an energy density, strictly speaking, is going to be kt delta f. And then you look at that and go, hang on a second here, but this is an energy, and the units of a change in frequency is a hertz, so that's in fact dimensionally the same thing as power. So that energy density is an energy density per unit time, because you're thinking about it in terms of frequencies, and so this in turn turns out to be a power. And now we can relate this is the RMS power, and so we can simply say kt delta f is the same thing as we had up here for the voltage RMS squared. And so the voltage RMS becomes 2 times the square root of R kt delta f. And in order to understand what this means, what we're saying is that any resistor intrinsically, if it's not at 0 Kelvin, is going to produce voltage noise, and the RMS voltage noise is going to depend on the resistor, the temperature, and also the bandwidth that you're doing the measurement in. So in other words, how long are you looking at those voltage fluctuations? So if I look at those voltage fluctuations for a long period of time, so that I'm using a small bandwidth, I see a smaller RMS fluctuation than if I look at a very, very short period of time. And that seems slightly counterintuitive, but it's true that the voltage you see gets, the noise you see gets worse the shorter, the quicker you're trying to do your measurements. And so trying to do measurements very, very quickly is noisier intrinsically than trying to do a very, very slow measurement. And this result is going to get very important later on. So as we saw, thermal resistance, thermal noise always occurs in resistors. So if you have a resistor, you cannot escape the fact you're going to get some thermal noise. The next thing we want to look at, however, okay, off we go. So what we've shown is that if you have a resistor, you're always going to go and have some kind of thermal noise. Now, actually, again, in real systems, we don't just have resistance, we have other forms of impedance. So we have things like inductance and capacitance. And so we need to go and take that into account. So what we do there is we replace the resistance R we had with the complex impedance. So for example, if you're including capacitance, it would take this sort of a form. The analysis is then similar, but it just gets a little bit more complicated because you have to remember that that means your impedance itself is now frequency dependent. But what you end up with, if you go crank through all the analysis, still ends up determining that your noise still has this factor of 4R KT in the square of the RMS voltage noise, but you have an additional factor which takes into account the capacitance, which again is going to be typically dependent on the frequency. And so what you tend to find is that in fact the noise gets worse if you have large capacitive or inductive impedances in your circuit as well. Okay, so that is a form of noise that you can't get rid of. It's intrinsic to all electrical circuits, but it depends on the temperature. There's, however, then another complication, and that's an effect called shot noise, or sometimes called flicker noise. And this is a form of noise which is not dependent on the temperature at all. So one illustration of how you can actually get, or how this noise appears, you would actually get if you look at any kind of photography process. So a photography process doesn't really matter exactly the details of how the image is being recorded, but it's going to involve some process which is going to take whether a photon did or didn't go and interact with a detector in some form. And what happens here, you can see, is that we're taking the photograph of an object, and we've just changed the exposure time to the detector. So as you go from the top left to the bottom right, all that you're doing is increasing the amount of time you've let it interact with the detector. Now, what you might trivially expect to happen here is that simply what's going to happen is the picture is going to go from being total black to brighter and brighter and brighter as you've had more time to collect more photons and average them out. And kind of if you look at the first and last images, that seems to be what's happened. But if you look at the images as you just start to reveal the details, you go from the image at the right on the top row to the first image in the middle row, you see it's not just getting brighter, but also there's kind of a graininess or a speckle to the image. In other words, you've got some noise in there. And the question is, well, how have we introduced that noise? And what's going on here is that you have a process where the thing you're measuring is quantized. And so there is then the effect of, within a given time period, did you or did you not go and see a signal? And so a common example you get this in electrical circuits is you get some kind of, say, for example, tunneling process, and we're actually able to count single electrons tunneling through a barrier of some description. And so what happens as electrons come through, you get these pulses. Okay, so the derivation then of how to go to this intrinsic pulses of current to a noise is beyond the scope of these lectures. So I've given you a reference to paper which does this. But broadly speaking, again, we can think of these things as being a series of current pulses on top of whatever background current you're measuring. And that effectively means you can think of that in terms of being an oscillating current going backwards and forwards. And again, we can then, from that, think about how the oscillating currents will appear as a frequency. Let's say if you crank through the analysis, what you discover is that you have a fluctuating current that then goes as the square root of the bandwidth in which you're trying to do the measurement. So again, just like the Johnson noise is appearing as a square root of the bandwidth you're using for the measurement. But now what it is it's got in it the size of the individual charge carriers you're dealing with. And so what you end up with then is a noise, and it gets worse as you've got a smaller signal, because then the sort of size of an individual charge carrier relative to your number of charge carriers you're trying to measure gets worse. So this is again an effect that you can pick up. However, even if you take all those things into account, what you then discover is that for many, in fact, probably nearly all measurements you can possibly go and do, there's another source of noise on top of this. And this source of noise has an amplitude which does vary as the frequency. So it goes as the frequency you're trying to measure, not the bandwidth you're measuring it in. So the difference here is that this just simply depends on the frequency of the measurement, but not on how long you spend trying to do that measurement. Now, this was originally thought of as some manifestation of shot noise, because it was initially discovered in things like semiconductor devices and particularly in vacuum tube valves. So it was first observed in the 1920s by Johnson looking at vacuum tubes. It was also found in various semiconductor devices, and Schottky, who invented the transistor, spent a lot of time observing that he did this 1/f noise in his devices. But actually, since then, it's been found that it appears in all kinds of physical and biological systems. So a range of things from human hearts, various, biological systems of squids, to give an example here, but things like brain magneto and electroencephalograms, but also bizarrely things like if we look at the distortions of sound being transmitted in the concert hall, it gets 1/f noise in it. And even more bizarrely, if you do an experiment asking people to go and estimate the length of a duration of time, they produce 1/f noise. So it's a really ubiquitous source, and unfortunately nobody really understands why all of these different ways you can generate noise all end up giving you a 1/f source. I mean, there are various esoteric theories put forward involving string theory, but realistically nobody actually really understands the origin of 1/f noise. It is just something that we observe in systems. Okay, so those are three different types of intrinsic noise. Then on top of that, there are extrinsic sources of noise that arise from how we set up our experimental environment. And so I already discussed some of this when we talked about cabling in the first of these set of lectures. We talked about inductive pickup, so mains pickup, which is what happens when you have a big loop of cables. Your plus or minus cables for doing a measurement are widely separated. And the problem is not just the 50 hertz of the main signal. So a main signal itself is a fairly good approximation to a sine wave. So the only frequency you expect to see there is the 50 hertz sine wave. So if you think about how you'd write down a Fourier series for a main signal, then your repeating oscillation is in fact just a sine wave at the fundamental frequency. And so you don't need to have any harmonic terms to describe that. The difficulty is that in reality, a piece of equipment will be often converting that mains frequency to a DC signal, to a DC voltage in order to run the equipment. And one of the most common ways that people do that is with the switch mode power supply, which is essentially turning on and off at the mains frequency. So they have something which is turning on and off at 50 hertz, which means that the interference signal is not a nice sine wave, it's a square wave. And again, if you go back to your first year maths and think about how you write down a Fourier series for a square wave, then you realize you have a lot of harmonics there. And so if you actually measure the interference signal as a function of frequency, you tend to get something like this, and you see that it's got a whole series of frequencies which, okay, these are plotted on log scale, but they are in fact appearing at every 50 hertz, so 50, 100, 150, 200, and so on, and going all the way out to a large frequency. So that tells you that, for example, doing a measurement at a multiple of 50 hertz is a really bad idea, because you're going to simply pick up the harmonics of the mains wave, mains power supplies, and that's going to be picking up all the noise from things like switch mode power supplies, which appear in things like computers and a lot of electronic instrumentation. And then, of course, the other end of the spectrum, you have various RF sources going on, mobile phones, Wi-Fi being the kind of most common examples, but also, again, you'll find other parts of the electronics are going to be driven. So, of course, computer, typical microprocessors run at a few gigahertz these days. So, again, that's a rather nice little RF interference source that you have going on because you have a digital computer turning itself on and off with a clock, and the clock is running at up to a few gigahertz. So there are all of these kind of human interference that you need to think about. And if possible, these are the ones you can eliminate by some of the techniques we're talking about to do with cabling. And then, of course, there are other interference sources that are not sort of intrinsic to the experiment, but they're intrinsic to trying to do an experiment in the real world. So because these sources were traditionally thought as being atmospheric sources in the radio industry, they got coined the term spherics as an abbreviation for atmospherics. And of course, the magnitude of the interference source will vary, as will the distance at which it is away from you. So, you know, locally you've got some kind of interference sources from things we're talking about, so other equipment in your lab, people doing experiments in the next door lab. And then we'd already mentioned the effect of atmospheric interference in terms of things like thunderstorms and lightning flashes. But then, of course, you've got effects due to solar activity. So the sun is a source of charged particles. Those charged particles interfere with the magnetic field of the Earth. And you get things like the northern lights as those charged particles from the sun interact with the atmosphere. But those in turn are actually generating electrical interference. And then over the course of a few years, you go through a solar cycle. The amount of sunspot activity, for example, waxes and wanes. And so you have some kind of very large scale interference effects. And of course, some of those interference effects from the sun can be enough to cause serious disruption to telecommunications on the Earth. So in principle, you know, you have to be worrying about, if you're designing a telecommunications system, that your solar activity could knock out your communications. But of course, what's actually going on there is it's just simply a huge interference source. Going beyond that, of course, we have galactic sources, so things like Sagittarius A at the center of the Earth, at the center of the Milky Way, which is a supermassive black hole, and is giving you a huge amount of interference there as well. And if you go beyond that, then there are things like the cosmic microwave background, you know, which is which is a universal scale interference source, and again, cosmic radiation coming from the origins of the universe can interfere with your detectors. And again, we've talked about that a little bit in the spectroscopy lectures about how cosmic rays can give you dark counts on a photomultiplier tube system. And again, a cosmic ray landing in your electronics, if you're a suitably sensitive electronic circuit, gives you noise, gives you interference. So really you are having to worry about potential interference sources across all scales. So I mentioned the problem of solar activity. So this came to bite in the 19th century when a powerful solar storm knocked out telegraph signals, which was state-of-the-art communications of the day. And basically it was generating such large electric fields, it was even, not only was it rendering some of the telecommunications unworkable because you simply had too much interference, it could even induce sufficient electric fields in the pickup apparatus that it would go and give the operators electric shocks. And these days, if we had an event that size, of that sort of magnitude, the amount of disruption it would cause to modern telecommunications would be massive. I mean, it's no coincidence that during the Cold War, it was proposed that one of the effects of nuclear weaponry would cause such large electromagnetic pulses that it would not only be contending with the physical disruption, but you'd also be contending with the fact that you just take out all the telecommunications as well. And for example, if you launch a satellite, a communication satellite in space, you have to radiation harden the electronics in the satellite because you're sitting above the Earth's magnetic field, outside of the shielding that gives you, and so you have to deal with the effects of radiation from the solar wind to a much larger extent. So of course, what you can do about that is to go and do a certain amount of shielding. So again, we've talked about the point about screening cables, so using coaxial cables or screen cables. What you're dealing with, what you're using here is the fact that an AC voltage is going to get damped in a conductor over some kind of characteristic length, which is given by its skin depth, which is frequency dependent. So depending on the frequency you're trying to screen out, then you need a different amount of screening. And in particular, if you're trying to deal with screening out radio waves, you don't even have to have that screening, doesn't even have to be continuous, because it also depends on the wavelength you're dealing with. So for example, screening on a mobile phone, where you're just trying to stop the radio frequency signals that the phone is working with from leaking out of the phone and into the ear of the user. The screening you need on a mobile phone doesn't even need to be continuous. You can perforate it, and it's still just as effective. Often what we do with an experiment, if we're being really worried about the noise, is we do it in a screened room. So in other words, you have a porta cabin effectively that is comprised of several layers of good electrical conductor, so copper sheeting, and you make sure that the door is connected to that electrical circuit. And you'd also, in order to avoid inductive coupling from magnetic fields, you also put in some very layers of soft magnetic material, so that the any magnetic field is essentially confined to your soft magnetic layer. So it's preferentially the magnetic field will go through the soft magnetic layer and not through the inside of your room, and so the room is very, very quiet, even from inductive pickup from mains fields. And then of course inside your room you have to be very careful you're not introducing any noise sources, so you make sure you leave your mobile phones outside, but also you run all the equipment inside it off battery packs, so that you don't have a 50 hertz main signal. Everything is being run directly from DC batteries. So if you go into all those sort of things and you measure the noise spectrum, you might get something like this. So this, in fact, is some data that I took when I was a postdoc, and I was measuring a superconducting quantum interference device. And so what we're representing the noise is a magnetic flux noise. But the reality is what we're mainly doing is picking up electrical noise and then just representing it as the equivalent magnetic noise. So this was a measurement that was done in the screened room, which is why there isn't a big noise spike at 50 hertz, 100 hertz, and so on. That showed that our screening was working out. But even so, we still have noise present. So in these sorts of plots, we plot everything as whatever the thing we're measuring per root hertz. And that's because things like Johnson noise and quantum shot noise are all dependent on the bandwidth per root hertz. So this is then going to mean that whatever signal we're measuring is going to be flat if we're looking at Johnson noise or quantum noise. So what we observe then is we have some 1 over f noise. So that's this decaying signal. This is plotted on a log-log plot. So if one works out that as a gradient of -1, and that carries on down to some level. And then at higher frequencies, the noise background becomes approximately level. And that's the sort of white noise background. So this is the effect of Johnson noise and of shot noise. So it doesn't matter what frequency we're at, we still measure noise at a fixed level per root hertz of bandwidth. However, if you look carefully in the signal, then there are some spikes at a few low number of kilohertz, and they're in fact coming from the electronics. So the electronics being used to measure this has some digital signals going on which are being processed at a few kilohertz, I think some of the signals we're seeing here are probably from the serial port that's being used to communicate with the computer that's recording the data. So that's what those spikes are there. And then finally, you see you've got this big sort of wide, broad peak and then a drop off. Now that's actually an artifact of how we did the measurement. So that's in fact the measurement electronics failing to record the signal. And so what you get is you get this sort of artifact appearing. So if we didn't have that and we had perfect electronics, what we'd see is the white noise would just carry on to the level indefinitely out as we went to higher and higher frequencies. But yeah, this is typically what you'd expect to see is the kind of background of your measurement. And I should say here, because I'm measuring this squid, as I talked about in the spectroscopy lectures, this is a particularly sensitive detector of magnetic fields. And so the reason we're measuring its noise is to see just how good a detector of magnetic noise we actually have here.